All right, welcome back to the compiler. This will be part 3 on generics, and I actually wrapped up the work offline. I can't always record when I work, either because I don't have the space or the time, or someone's watching TV in another room. But yeah, wrapped up the work, and I'm going to walk through. There really wasn't much left at the end of the last video, so hopefully we can make this a little bit continuous and not leave anyone hanging who wants to sort of see the whole implementation. But I thought I'd start with the end product, which is this generic struct program here, where yeah, we have our box of T working, and we also I did this mbox, which I was thinking like multi or something, but it takes a T and a U, and it doesn't just feature the T as is, it features an optional T. And even though you see T question mark, really this is more like this. So it doesn't see T, it sees optional, and then it has to recurse in and then do what it needs to do for optionals, and then eventually it sees the type variable and substitutes it, and then we also have the U. We also associate a namespace with this and create a function called T, which returns the T. So when we call T, I'm looking down here seeing that yeah. So that's a field access. When we call the method T, that should return an optional T, in this case, it's going to be an int. So I don't think I have an assertion on that one, but the point is that you can call it. I think it does work. My mouse movement's like really laggy. I wonder if my computer, if I need to close a few other programs before I continue. One sec. Okay, I think that's better. Yeah, let's look at this. So we make a box event, a box of bool, box of bool with a different value, box with an optional bool, box with a bool pointer, or bool reference, I should say, and then all the assertions. And then now we have our mbox that's int bool. So this is actually an optional int. We can see that it's an optional int because we're able to call, use the unwrapping operation on it. This wouldn't compile if T were not an optional int. And then U is a Boolean. And then we're able to call this as well, and we can go ahead and assert this returns T. So this should probably assert that that's 0. What we can do is compile this. We can run file here. As long as I wasn't in the middle of something. Ooh, yeah, I was in the middle of something. Definitely not in a working state for demo. One sec. Okay, we're back. So we're not type checking here. So let's unwrap that. And then they'll both be 0. And we can see that we run successfully. We can see here I left some debug info in that I'll remove soon. We can see we're generating a generic wrapper for a value T with companion space none. Here when we do it for mbox, there is a companion namespace because this is the companion namespace of mbox. And here's our substituting. So T for T, interestingly enough, I'm actually not sure why that's happening in the U for U. Oh, okay. It's when we evaluate this function, I think. Yeah, and we need to instantiate an mbox of TU so that we can work with this, and that just works as well. But once we get down here to the actual instances, an int for the first T, that's this one. We should see a bool, and then it doesn't happen again because it's cached. So there's only one box of bool. And now we have bool optional, bool reference, and bool T and U for mbox down here. And it passes. If we dumped out the types, I promise you there's only one box of bool. And the reason for that we'll get to when we look at the code in a second. Also have generic enum. I just went ahead and did result as my test type. It doesn't exercise a lot of complexity because the type variables just appear in the top position, but I'm not too worried about it working, because once we're in here, then it's no longer calling the enum code, it's just specializing the type inside, which is pretty well exercised in the other function. And if there's problems, I'm sure we'll find them. But anyway, so result has a show where if it's okay, it says okay, and then the value. Now note here, I've only implemented show for result int string. This is a little weird. You would never really do this. You would make this generic, but I don't have a way to say type variable t where t is toStringable just yet. I mean, I do have the traits or the abilities for it. I just don't have a way to actually specify the constraint, and that wasn't really my goal to test. Anyway, we have a method. The point is to be able to call the method, even though it's on a specialized version. So anyway, we make 2. We have result int string. Yeah, we have an OK and an error. We call x1 show, x2 show, and I did size of and alignment of well, offline as well, which was a lot of fun to get working. Maybe I should do a video on that, but we can see the size of this is 24 bytes, and then 8 bytes for the alignment, because basically you get a 64-bit discriminant, and then the payload is the size of the longest. So since E is a string and that takes up 128 bits, you end up with 24 bytes, or 192, I think, bits there, 64 times 3. And yeah, since each segment's 64, that's your alignment. That is working. Yeah, so if we go to typer, I think we'll see, so the method we were in is eval type application. This is the function that we made for this purpose. Let's just walk through it. So yeah, I'm just trying to decide where to start. We do the lookup of the type, the base of the application, and now our goal is to create an instance of it given the type parameters that have been passed. So the first thing we do is evaluate the type parameters. That gives us a vec of type ID. That's just calling eval type expr, nothing really special going on there. And then we expect that the base type is a generic. Now we could do this first actually, because it's a failure case. Nice little performance trick. Don't do unnecessary work. I think we might just have a borrow issue though. Yeah, we do. But I am going to we could just reborrow, right? This lookup is really cheap. This evaluation of these type exprs could be a bit more expensive, and the allocations and stuff. What we can do is, instead of gen.clone, it's just going to be self types get type ID again. In this case, we don't even need to bind gen. We can just say like, hey, we're checking that it's generic, and then let gen, and that can be expect generic. We'll leave Copilot on tonight and see what happens. So we're just gonna say, yeah, I want to generate that method, and then we'll make sure, I think it should be public. And let's put it though with the other, like expect struct as tag expect generic. And of course, generic type, that is type. All right, Copilot. Is that how I do it? Yep, that's how I do it. All right, so now we'll just go back. Sometimes we just gotta, okay. And we were cloning it because we didn't want to have a borrow. So I think we do need to clone it, because we're gonna borrow self-mutably down here. Okay, so we have our generic base, and this is what we did in part 1. We're going to grab its definition info and we're going to alter it. So this is what I've done. So we do put definition info on the children, but we also put this new thing, which is generic parent. So all the instances of box from, for example, our generic struct, that's not the one I meant to do. I wanted that one to switch. All the instances of box point to generic parent of this type here, which lets us know where they came from. How do I go back? Eval. Wait, there's a ghost symbol. Eval type. Application. We'll get down here. Okay. Okay, and let's give ourselves our space back. Okay, so we have this definition info patched and ready to go. That's gonna matter later, I think. Yeah, I think that's a bug. I think I added it for bookkeeping. I know I'm not depending on it yet. We are depending on this definite info for the companion namespace, but yeah, I don't think I was passing the right one. So now we have the one that we've modified with the generic parent. So that's great. But anyway, so we actually have also added to our generic wrapper type, we have known specializations. So once we've already specialized it, we store, we say, hey, last time the user passed int to box, this is the type we made. Last time the user passed int bool to inbox, so this could be int bool. This is the type we made. So if we find one, then we just return it. And so we'd only have to do the work once. If we don't, then we do the work and then we do update the hash map. And then that's the whole thing. So all we have left to do is read substitute in type and understand what's going on in here. So what are we passing it? We're passing it the inner type of the wrapper, right? So in that case, that's going to be like this type, the thing we need to specialize. The defin info, which we just fixed. Evaluated type params. These are the types that were passed. So in our examples here, int bool, sorry, vec of one int, vec of one bool here, or here eval type params is a vec of two type IDs and int bool. Hope you get the idea. And then the parameters of the general type. So think of these two vectors are always the same length and they go together. You would like zip them up. And you have on the left-hand side like the generic variable and on the right-hand side what was actually passed for it. So you would have like, you know, tu, and then you would have int bool. And then, so we know t equals int, u equals bool. And so those go in tandem. And then the type application ID for error spans and stuff. So what you'll see here is that we kind of zip these the pass params and the generic params up together. And now it's just a case of doing the substitution. Like it's very intuitive in your head. If you just look at this type, you just replace all the t's with what you're replacing t with. And that's it. So you kind of recurse down until you see the type variable. This is the key type to this whole thing because once we get to this is what we substitute. So here I do the lookup to find the variable matching the name of this type variable. And this is where we grab the past params by the index and that's the corresponding type, and we return that. And then we just return, and since we're recursing, that just returns up the chain up to whatever we were in, as you can see here. So like for an enum, we have a bunch of payloads. For each payload, we just call substitute in type, passing down everything. No defin info for the recursive cases because we don't need to attach any definition info to the like types inside the type. Only the root one that we're actually going to have references to that the user can actually refer to is plenty. And then we're doing some stuff where we don't want to do unnecessary work. We don't want to make all these new types that are identical. So any changed false. Every time we do this, substitute in type is very much welcome to return the same type if no work was done, and that's fine. So we say, hey, if the thing that came back from substitute is not the same, then we say any change true and we update the payload, and then only if any change do we make a new enum and add it to our type pool and then return its ID. Otherwise, if we nothing changed, then we just return the type we had. So it's gonna be, you know, pretty fast and pretty efficient, and we'll only ever do the same specialization once. That's enum. That's the hardest case because it's got all these variants. Every variant has a payload. Reference is pretty simple. Reference only has one inner type. So we just specialize the inner type, and then, hey, if we did any work, look at the same thing, add this new optional with a specialized inner type to the pool and return that. Otherwise, return the old one. Optional, the same. Sorry. Oh, this is embarrassing. That's, yeah, I guess I didn't test specializing references that well. I did this. I did specializing optionals, but I didn't ever put a reference in there. That would definitely have blown up the world. So there we go. We caught a really bad copy paste bug there. That's what's really embarrassing about it too, that it was so obviously copy paste. And now we have a struct. So struct is exactly what you think. Hey, any change false for every field. Do the thing. If it changed, any change, update the field types so that if anything changed, we can make a new struct type with the new fields with the defin info we were given. The AST node, this is like where it was made. So we're going to like point to here for where this instance of the type was made. Yeah, and then we return that. So we've called substitute in type, and we can go, you know, back to here. Remember, this is eval type application. So we got this far. We knew that all we had to do was specialize the type, and then we return it. And then that gives us a type ID to work with every time we see generics. And that completes the picture. Let's test with a reference. So this would be another way of, instead of the built-in syntax, talking about a reference. Let's say val r. So the only way to get a reference right now in this language is to use this ampersand, which is address of, like in C. And it actually does just take the stack address of the thing, which is really broken. I don't even know if I want that in the language. Eventually it will be whatever I end up doing for new or alloc. I want to do allocators of some kind. But anyway, right now, the only way to get a pointer reference to something is to use address of. So we do that. And this type, this is just a type alias. So I'm not sure if it's gonna complain. I've honestly only done it with structs and enums, which like make a fresh type. I have no idea how this is gonna work with just a type alias like this. But then we could assert that yeah, that would be equal to 0 equals for in star. So my dereference operator has like some crazy precedence where nothing works unless you explicitly do the parens. I think the way it parses by default is literally this. Because it said that there was no dereference operator defined on you know, I'm not sure. This worked. Generating a generic wrapper. Okay. Right. So it's a third or fourth type of type definition that I've had here. So there's the opaque aliases. But if you do this, then yeah, I think generic works. Let's go back to eval type definition. Refresh how that works and try and understand why it works. It makes sense that I didn't test it, that I had confidence in it if it's already handled. I think if I knew it wasn't handled, I would have tested this explicitly. Okay. Where's the opaque? Not opaque, but the generic. Okay, here's the generic case. So if it has type params, then okay, we don't do any of the alias business, the other stuff that applies. We do this generic route and we have the wrapper. And so all types are handled the same. Structs and enums are not special. So that's why we're able to do a ref of T. That's really neat that just works. We could try something pathological. So we could do an enum with one variant that has an optional pointer to a T. And ref of int will then need to be dot thing. Yes, it will be sum of let's see, the address of value, and then we dereference it, and then we will we could do this is sum 0. This works. I'm flying high. Okay, got question mark. So I don't think we even parse multiple postfix operators because I didn't want to even think about this. So I just don't even parse them. Oh, that's really sad. And I don't think I can get around it by using parens because I don't think I've done that for type expressions yet. But all is not lost. Well, do I dare make an intermediate type to get around it? Well, instead of using reference, let's do something like struct. So we'll have an optional T inside here. So instead of reference, and now ref is a bad name. This needs a struct with a field called T, which is an optional int. I'll go ahead and explicitly specify it. It should actually infer for me. And then we're going to say that cert R. So I need to cast it to thing. Is we'll test our pattern matching. No type name thing is in scope. Impossible pattern, a match target thing is not a struct. But the payload is a struct. T is sum 0. Well, this was supposed to be a demo, but now we're fixing shit. I think it's okay. I don't know why that assert failed. I'm proud that this line compiled though. If it wasn't the payload, then we need to be matching. Okay, I was dumb. I don't need to cast it because I can pattern match on the enum. Okay, it works that way. but if we call .payload for some reason, it doesn't. So let's do this. Let's print int, yes, r.asThing.payload, which should be a record.t bang. Yeah, that's what I want. Thank you, Copilot. Okay, that is not 0. So that's a bug. Pretty bad one. I don't think it's a bug with generics though. Well, we should try to repro that. So is it with the cast or is it with .payload? Type checking's all working though. Love that. Let's keep the one that works. Comment out the one that doesn't. I don't think there's much else to show. I think that's it for generics. Nothing to do in CodeGen here. We're completely handling it. These are just concrete types by the time we get to CodeGen. So yeah, I hope that wraps up the story. Obviously, it's not like a complete and finished and bug-free implementation, but I think the bones are definitely there. That is the main idea, all completed and working for all types. I'm sure we have some bugs, as we just fixed a few. Pretty lame bugs, to be honest. But yeah, I think that closes that chapter. Thanks for watching. As always, if you made it to the end, I hope you learned something, and yeah, best of luck in your programming adventures. See you next time.